So we talked a little bit about the three carbohydrates, right? The 3 carbons, 5 carbons, and 6 carbons. We talked a little bit about how fructose is a structural isomer, galactose is a stereoisomer of glucose, a non-mirror image stereoisomer of glucose. Now, what I wanted to do is I wanted to talk a little bit about this numbering system. So you notice that you see the little blue numbers all over the place. And so a lot of times that kind of confuses students. And they're like, okay, what's the deal with all these numbers? And so here's glucose. So we're going to just kind of simplify it a little bit. So take all the rest of them off of the table. First of all, just take a look at glucose. Everything you're seeing here is glucose on this particular image. Is just different ways of looking at glucose. And so the whole point of this one is to kind of show you how glucose makes a ring and the carbons that are involved. So one of the things you'll notice over here on the left, this is what's called the flat diagram. Oftentimes you see this in carbohydrate biochemistry. And so there's lots of different carbohydrates like this. And so the flat diagrams look similar to this. And there's a couple advantages to this, right? So in this case, when you're taking a look at the ring, remember we talked a little bit about how galactose and glucose only differ by the orientation of their hydroxyl groups, either above or below the ring. When you have it in a flat diagram, it changes that above and below to right and left, right? So that's kind of what it changes to. So you can see here, glucose is going to be right, left, right, right, right. Now, what they're trying to show you here is who all's involved in the process of glucose forming a ring. So what happens is this oxygen here from carbon number 5 will actually come in here and attack the carbonyl carbon. Now what that does then is it forms a bond between that oxygen and the carbon. And since it takes that bond away, right? So if you did that, what you would be adding is a 5th bond to carbon, right? Because it's already got 4, right? It's got 2 with oxygen, 1 with hydrogen, and the other one with the chain. So if you added another bond here, somebody's got to go, right? 5's too many. You can only accommodate 4. So who goes? Well, as it turns out, the one that goes is one of the oxygen bonds. So one of these electrons will go back to the oxygen, turning this into a single bond. And then generally speaking, the hydrogen will take those electrons that get booted back onto oxygen. And that's the reason why you get this sort of situation here. So here you can see it's basically turning itself around. You can see the oxygen is going and attacking that carbon. And when it does so, then those electrons are going to go back onto the oxygen, and it's going to fill in and form a bond with hydrogen. So what that basically means is you turn that into an OH group, okay? From an oxygen double bond to an oxygen single bond. Okay. Now in chemistry, they've got an entire spectrum of oxidation states, right? They have this kind of thing called oxidation states. It's oftentimes associated with how many electrons you've got shared or how many oxygens you've got shared. So having 2 double bonds in there or having 2 bonds in there is kind of like having double oxygens. So you have a higher oxidation state than if you just had 1 single bond. And so don't lose too much sleep over that one, right? So what I just said right there, that just is what's happening when you're talking about this. If you're, by the way, if you're wondering what organic chemistry is like, this is what it's like, right? So you have one thing attacking another and you're following electrons as they sort of force bonds out, and then they kind of replace them. And so that's, you're drawing lots of arrows when you're in organic chemistry. Long story short, what this basically results in is a bond between carbon 1 and the oxygen of carbon 5. And so the oxygen actually becomes a member of the ring. Okay. Now, as a result, what that means is this group down here, this like little methyl group down here, this guy ends up getting pushed above the ring. So that's one of the reasons why carbon number 6 is out here above the ring. Okay. And everybody else is inside the ring. Okay. Because you kind of do that 1 to 5 connection. Now let's talk a little bit about this numbering system. That's all great if you're into organic chemistry, right? But now let's talk a little bit about this numbering system. So what do these numbers mean? Well, in organic chemistry, they have, potentially these long carbon chains, kind of like this guy right here, right? And there's going to be stuff attached to them. There's going to be some functional groups attached to them, and the problem with this is, it's like, well, wait a minute. So how do I know if you're talking about the hydroxyl group on a particular carbon, how do I know which carbon you're talking about, right? Because I've got 6 of them. Most of them have a hydroxyl group attached to them, right? So by telling me that you're looking at the hydroxyl group attached to the carbon, doesn't really tell me much, does it? It narrows it down to 6. And so the question is, which carbon are you talking about? Well, in order to understand which carbon you're talking about, the organic chemists numbered the carbons to kind of give them a sense of identity. Because that's actually what the carbons, the way they actually behave. Because each one of these individual carbons, even though they're carbon, because of the specific atoms that are in and around them, they have kind of a slightly different sort of a reality, right? Think of it as sort of like living on a street around neighbors. My everyday existence is largely within the framework of the neighbors that are around me, right? So I've got one neighbor to my left, one to my right, and one across the street. And that kind of forms my major interactions. Well, that's kind of a little bit different than the person who lives next door to me, right? Because I don't know the neighbor that's on their other side. And so that's not part of my reality because I don't really talk to them a whole lot, but they do, right? So their reality is a little bit different. I mean, I'm part of their reality, certainly, but then this neighbor that I have no function or association with is part of the reality too. So for them, even though they live in the same neighborhood, their reality looks a little bit different, right? So maybe I'm a fairly relaxed, laid back sort of a guy, which I tend to be, right? But maybe the other neighbor is like just a total a-hole. And it's like, if you're not out there in the middle of the heavy snow shoveling the sidewalk, they're like calling the police on you. Isn't that lovely? Right. Right. So that would qualify for a-hole territory, especially after you mentioned to them that you've got 24 hours by city ordinance to clear your sidewalk. Even then, most people don't do that. Right? Yeah, the city doesn't care. The city is, I mean, unless you have like, masses of people dying in front of your house because they're slipping on ice, then nobody cares. And some neighbors would be like, listen, I put an orange cone out there, done. Right. So we got to clear those in our neighborhood. I'm like, okay, so granted, I'll give them a break. They're like super old and decrepit. I'm like, okay, so yeah, you get a pass on that one. But when I kill myself in front of your house, okay, it'll be different, right? Because you may not have to work for a living, but I do. Which is actually little, but a bunch of old people live in my neighborhood. So I'm like the youngest of all of them. Like the young punk. So what they do then is they have to figure out a way to number, right? So for instance, how do you know that you start number 1 over here at this carbon? Why not at this one down here? Well, what organic chemists did, they realized this problem. And what they did is they took all the functional groups that some of them we talked about, right? So hydroxyls, carbonyls, carboxylic acids, things like that. Plus all the rest of them that we didn't talk about that is on their list of things they study in organic. And what they did is they ranked them in order of priority, right? So there are functional groups that have a higher priority than others. And if you have a high priority functional group, then the carbon that you're attached to is like the king. You're like number 1. Now, as it turns out, the carbonyl is fairly high on the list, okay? Which is the reason why you start number 1 at that carbonyl. Notice it is in the form of an aldehyde, right? That one? Ooh, no, that's part of hurting brain space, right? So carbon chain coming into the carbon, there's your carbon double bond, right? Or your oxygen double bond, and then it terminates in a hydrogen. So that would be an aldehyde type of carbohydrate. So in this case, since carbonyls are fairly high in the pecking order, we start number 1 there. So that way, when we're talking about the hydroxyl group on carbon number 5, we know exactly which one we're talking about. Okay, that's the one that's involved in the ring. And so you'll see this actually terminology. It's an organic chemistry thing, but this is just basically to allow us to be able to know exactly which carbon we're talking about when we're talking to each other about these different things. By the way, this is also what we're talking about whenever you look at some sort of a molecule or something like that, like in insecticides or pesticides, something like that, you see this like, 1, 2, 5, 4, or 4, 5, tetramethylene diamine, some big monsters. Those numbers are associated with the numbers of the carbons in the backbone. And then the things that come after it, tetramethylene diamine, are the molecules, the functional groups that are attached at those points. Okay. And so it kind of helps us to be able to organize ourselves. And we'll see that numbering convention, utility of that numbering convention a little bit later on when we kind of get a little deeper into the carbohydrate section. Now, the other thing we also want to mention is that when you're actually forming this ring, you can have basically two different orientations of the hydroxyl group. One of the orientations will be to place a hydroxyl group below the ring. The other one will be to place a hydroxyl group above the ring. As it turns out, they're both glucose, but they're two different forms of glucose. So the one that is below the ring is alpha glucose. The one that is above the ring is beta glucose. And they're not the same. They look the same, but they're not the same. They do have some important differences, and we'll take a look at what those differences are as we start to unpack and sort of sketch out a little bit more the nature of carbohydrates and how you're putting them together. Okay. So just to add more pain for the flat diagram, so to speak, this is kind of an example of the flat version. So we saw like the little cyclic version of fructose, glucose, and galactose, the set of isomers. So this kind of shows you the flat version of these differences. So remember, fructose is the structural isomer of glucose, right? These are all, by the way, C6H12O6, right? So those are all the same that way. But if you notice, fructose is not an aldehyde, is it? What is this? It's a ketone version, right? Side chain coming in, side chain going out. So here's your side chain coming in, side chain going out, and you have your carbonyl right there. So that's an example of a ketone type of carbonyl, right? So we call this a ketose, or a ketone formed carbohydrate. Then glucose and galactose are both aldoses, right? You notice you have carbon chain coming in, terminates in a hydrogen for both of these guys. This is your carbonyl bond. So these guys are aldoses, aldehyde form of carbohydrates. Now, when these guys when you're looking at the differences, you notice there's only one difference here, right versus left on the hydroxyl. And that's what creates this idea that they're stereoisomeric, not structurally isomeric. And so you can see that they're largely the same. You just have a little flip in that one area. That's what makes them a stereoisomer. So that's kind of our monomers, right? Those are our big ones that we cover. There's lots of other types of monomers as well, right? So you got fructose, you got galactose. There's a couple of other types of monomers that we can talk about, but they're not really prevalent in biology. These are probably the big three in biology: fructose, glucose, and galactose. But the disaccharides are actually, there's a lot more that you can do with the disaccharides, and they have much more biological capacity. So now that we have our monomers down, right, we have three different types of monomers. Let's go ahead and start putting them together, right? We have our systems, don't we? We have our functions in terms of how to put these things together now, don't we? We've got dehydration synthesis and we've got hydrolysis. So we can put them together and we can take them apart. So we've got that mechanism in place now. So now what we want to do is, now we have our monomers outlined in terms of our monosaccharides, let's start putting some of them together. Which reaction we're going to use? Oh, I got both of them. So yes, we're going to start putting these things together. So which reaction are we going to use? Dehydration, right? Synthesis, right? So hydrolysis takes them apart. Remember, hydro, water, lysis, to cut. So water cutter. Versus dehydration synthesis means you're putting it together and you're losing the water in the process. So let's take a look at this. So here you can see you're going to take two monosaccharides, right? Basically two bricks to build your brick wall. And then you're going to link these guys together with your dehydration synthesis. So down here you can see you've got not just any glucose, but you've got an alpha glucose, right? So you're kind of pointed downward. And you've got a fructose, right? That's your structural isomer that you're going to be using in this particular case. Now what you're going to do, remember, when you're going through a dehydration synthesis, you always have to have the component of water, right? Because that's going to be one of your byproducts. So when an enzyme comes in here to grab a hold of this, it's going to be looking for the components of water. Where does it find it? It finds it on the hydroxyl groups and the hydrogen groups that are already associated with these particular carbohydrates. For instance, this hydroxyl group right here on fructose is going to pair up with this blue hydrogen associated with glucose. Now what's going to happen is the enzyme is going to cut this bond right there. It's going to cut this bond right there. And then of course, at this particular point, what have we done to these molecules? Are they happy again? Are they happy? Not if we just did this, right? Because whenever you're breaking a bond, you are, well, not necessarily losing electrons, but you're no longer in harmony with your octet rule, right? So you're immediately in a state of disrepair now. So you're not happy anymore. So the question is now, what do I do, right? So you just basically took my thing away from me. Now I need some sort of satisfaction. So what do I do now, right? So the enzyme is basically going to say, listen, OH and hydrogen, why don't you guys meet each other and you head off as water. Now, glucose and fructose, I realize you're still unhappy because you didn't get anything yet, have you? So what I want you to do, oxygen from glucose, I want you to meet the carbon from fructose. And that becomes the new bond. So what you form then is a glucose fructose dimer, two things, right? And this right here is what's referred to as a glycosidic bond. That's, by the way, the type of bond that holds these carbohydrates together. In all these polymers, there's always going to be some sort of a name for the bond that holds them all together. In the case of the carbohydrates, it's the glycosidic bond. Think of it: glyco, glycogen, glycolysis, glycemic index for those diabetics who are trying to keep track of their sugar release, right? That's all root for a carbohydrate. Okay, so that's where that comes from, glycosidic bond. Now, what happens if I don't do fructose? What happens if I do two glucoses instead? The exact same process is the same. The enzyme is different, but the process is the same in the sense that you're still going to be cutting those bonds, forming a water, and then you're going to be reuniting the two monomers together. In this case, in the case of a glucose, you're going to have a glucose and a glucose, which is going to give you maltose. So sucrose, by the way, is to be found where? If I were to send you out into the world and say, give me some sucrose, what do you have to come back with? Yeah, table sugar, right? That's basically what it is. So what we actually associate with sugar, is that a question?
Yeah, just a question about the maltose. It's still a glycosidic bond with
Correct.
maltose?
Correct. Still a glycosidic bond. These are all glycosidic bonds. Right, as it turns out, these disaccharides, two sugars, so saccharin, saccharide is a root for sugar. These disaccharides are actually quite helpful because they circulate very, very well in your blood system. And so you tend to circulate your carbohydrates as disaccharides a lot in your sugars. And it's only later that they split apart into glucose and fructose to enter into your metabolism. So sugar, for instance, table sugar is perfect because you don't have to do anything to get that. It's already there. And so it circulates very easily through your system as a disaccharide. So there's a couple of others, right? So we talked about sucrose, we talked about maltose. What about lactose? So this one is a fructose glucose combo, right? This one's a glucose combo. What about this one? This one is a glucose galactose combo. So those two together, that's where your galactose comes from. And for those of you who are lactose intolerant, the reason is because you don't have an enzyme to break lactose apart. That's as simple as that. So your enzyme, well, you do have the enzyme. It's just your enzyme is either under functioning or not efficiently functioning for some reason. Okay. So not necessarily an uncommon thing, especially when you think of us in terms of being mammals, right? Because when you take a look at most mammals, we're the only mammals actually on the planet that continue drinking milk after the age of 2. Everybody else is all grown up. So we're still basically babies, right? So because we still drink milk throughout. So it's kind of natural actually for that lactose digesting component in mammals to sort of diminish over time, because the idea is after the age of 2, you're weaned. so you don't need it anymore. And so some of us are better at being weaned than others, right? So that's kind of where the root of that lactose intolerance kind of comes from a population perspective. So notice, however, you kind of structurally have a slightly different way of looking at things here in terms of the way these are broken down, these glycosidic bonds, that is, are broken down. So what I want to do is I want to add a slide in here. And I want to go over the different types of glycosidic bonds because there's different types of them. So we've already seen two of them. The first one is what's called a 1,2 glycosidic bond. This is where a 6-carbon ringed or hexagonal ring forms a bond between its carbon 1 and the carbon 2 of a pentagonal monosaccharide. So like we just saw, your glucose forming a connection between itself and the pentagonal ring. Why? Because as it turns out, this is carbon 1, 2, 3, 4, 5, and then 6 is above. This turns into carbon 2 actually. So carbon 1 is up here. So there's 1, there's 2, 3, 4, 5, and then 6 is above. So it's got 2 that are above. Okay. So it's to the 1,2 position. Okay. And I just didn't draw the extra branches up there. So this is basically what it's doing. So that is our sucrose formation. The second one is one we see mostly. This is the 1,4 glycosidic bond. This is where the carbon 1 of one hexagonal ring forms a bond with the carbon 4 of another. So in this particular case, this is what we have. There's our bond. So this is carbon 1, this is carbon 4. So 1, 2, 3, 4, 5, 6. So this one forms the long chains of things like glucose. So then the maltose is held together with the 1,4 glycosidic bond. Sucrose is held together with a 1,2 glycosidic bond. The last one is a 1,6 glycosidic bond. This is where a carbon 6 of one hexagonal ring forms a bond to carbon 1 of another. creating a branch. This is what it looks like. So I'm going to draw so there's my chain. Now, as it turns out, where this is 5 and this is 6. So if I want to form a branch, then there's another guy comes in here. Here's my number 1. And that's going to form a branch there. So it branches off. So then you can start to form a long branch off of this place. So you form a 1-6 by attaching a 1 to that number 6 position. And this forms a side chain or a branch. And so these are the 3 glycosidic bonds. So like I said before, we saw here that this is going to be a 1-2 glycosidic bond between the 2 structural isomers. This one here is going to be a 1-4 glycosidic bond between the 2 stereoisomers. Does that make sense? This one? And this is just basically a matter of how you're linking these things together. Just different ways to link together the monosaccharides. And it kind of creates different orientations, right? So you have to figure out a way to link together your structural isomers, a way to link together your stereoisomers, and then kind of a way to branch off. And the branching actually becomes pretty important because we'll see an example of where we get to see these branched carbohydrates. Well, you can see here that I've actually drawn now more than just 2 monosaccharides, right? So it's not a disaccharide anymore, right? This thing down here at the bottom is clearly not a disaccharide, right? So there's a lot more going on in there, which kind of brings us to our next stop. So if you go beyond 2 and you go into 3, 4, 5, 6, however many, then you're starting to move into the world of polysaccharides, right? Many saccharides is sugars. So these will basically form long chains, typically of glucose, that are all kind of linked together. And they're all linked together by the same process, right? They're all basically just doing a round of dehydration synthesis, just over and over and over and over and over again. That's all you're doing is dehydration synthesis. You're just kind of making this brick, this wall longer and longer and bigger and bigger. So you're just building your actual polysaccharide. Now, the reason why polysaccharides are important is because this allows you to be able to store them. Think about it for a second. Let's imagine you just ate a big meal. Okay, if it's fall, maybe we're taking a look at one of the big eating holidays, right? Like Thanksgiving, where we're basically putting away 3 birds at once. Looking at you turducken fans, right? So you're just annihilating 3 species all at the same time. Or hey, yesterday, unfortunately, was Chiefs Day. And I am proud as a Raider fan, I watched absolutely 0 of it. The TV didn't even come on all day long. That's how interested I am in the Chiefs. And I think I can find common ground with Broncos fans in that regard. And it's a good thing I didn't watch it anyway, because honestly, I think they should be stripped of the championship. Just because I hate the Chiefs. I'm just kidding. They should be stripped of their entire organization and liquidated. But that's hardcore right there, right? That's a true Raider fan coming out there. What we're really like on the inside. But anyway, no, because of slippery field and all that. So What, when the field basically negates half of your defensive strategy on the other side, then you're not legitimate. I'm sorry. As far as I'm concerned, the Chiefs have won 2 Super Bowls, not 3. Because this last one was a joke. And they're a joke if they honestly think that's legit. So they can stick that in their mustard and ketchup pipe and smoke it. So anyway, a little bitter. And I didn't even watch the game. I didn't have to, right? I mean, Raider fans come hard baked that way. We just come out of the oven like that, which is the reason why nobody likes us. But anyway, that's neither here nor there. That's my problem, right? I have to seek therapy for that one. That doesn't really affect you guys at all. And that's all recorded. Just saying, you might want to fast forward to that part. I tell you now that you've just listened through it. But anyway. Okay, good. It's like, so I can go back and rewind it and listen to it all. But anyway, that's that. It's like, I must have been saying something good. Not really. But anyway, right. So here's the thing, right? So the idea of Super Bowl is, you know, if you're hardcore, if it was your team, right? I mean, what are you doing like all day long? You're like doing the home tailgate, right? I mean, you basically start grazing as soon as you wake up, and it just kind of picks up steam. I mean, I lived through Super Bowl 50. I wouldn't know what it was like in Denver, right? I mean, you just kind of start, I mean, you just start gorging and you just kind of don't stop until like a week or 2 later. Well, because they won Super Bowl 50, right? So that's why you didn't stop. If they lost, then you would be stopping, and then you'd be in depression again. Right. But so the thing is, obviously, if you're like most Super Bowl fans, you've just eaten like enough calories to last you a month in one sitting. A couple of months, perhaps, depending on how that looks and how, you know, how foodie you are. So the question is, you just flooded your system with a ton of carbohydrate, yes? Are you gonna use all that? No, because what is the average Super Bowl fan's most like physical activity that they do on Super Bowl Sunday? That's about it, right? And even then, the beer's usually half gone, so it's not really much of a lift at that point, right? Otherwise, what are you? You're kind of like half asleep on the couch, especially if it's not your team. You're kind of like coming in and going out between sort of alcohol-induced fog, cursing every time you see red. Literally, of course, yesterday, right? You guys like, so are you trying to like confess to something? No. Like I said, the TV didn't even go on. I already knew who was playing. I could care less. It was over. So the season was over a long time ago for us. So here's the thing. Are you just so if you're not going to use it, what are you going to do with it? You're going to go to the bathroom and just unload it? Pee it all away? Dump it out? Is that a good use of all the glucose you just consumed? How easy it now? Stop thinking like a person. Think like an animal. How easy is it to come by that much glucose? Remember, I don't know if I said this section, but somebody, I remember saying somebody, we are the only species on the face of the planet that can eat at will. No other species on the planet has that capacity. For what? No. No, they eat because we let them eat. They wouldn't, if they were free ranging and wild, they wouldn't be eating at will. They would basically be eating what they could get a hold of, and they would basically overconsume, and then they would want to eat still, but they wouldn't be able to. So they can't eat at will. And the problem is mammals want to eat all the time. Cows would eat all the time if they could. But they can't because we only have limited pasturage. We're the ones that feed them and make sure that they eat whenever they want, not because they actually have that access. So for us, we can make the conscious decision, I want to eat right now. Can you go find some food and eat right now? Sure. There's a McDonald's on every corner. No other mammal on the planet, or animal actually on the planet, can do that. Because they have to go find it, and sometimes they can't find it, which means they're going to have to go hungry for a little while. By the way, if you're hungry as an animal, then you didn't eat at will. Right? No mammal except for us is willing to tolerate hunger. They could, if they could. They don't pass things up. Right? Just like, oh, hey, here's some food. I'm just going to pass this one up. Right? No. As soon as they see it, I mean, it's in there. Right? So we're the only ones that can eat whenever we want. But the problem is our bodies don't think that way. Our bodies still think like we're mammals. And so they're taking a look, they're like, you know what? You had a great meal today. It's unfortunate that you had to watch a bunch of ketchup and mustard all over the TV screen, right? Of course, if you're wondering, that's the Chiefs, right? Because literally they look like a half puked up hot dog. That's what they look like. They've always looked that way. Sorry, if you're a Chiefs fan, I don't take any of that back. I apologize, but no, I don't actually. Just like nobody in Broncos country would apologize for laying into the Raiders. I don't expect you to. But anyway, because honestly, we deserve it. But anyway, so the idea is you're eating great now, right? But what about tomorrow? Tomorrow, all the food could be gone. And guess what? You've officially started the famine. So those nice lush pastures that you're grazing on now are going to be gone as soon as the dry season hits. And guess what, cow? I can tell you right now, you don't have the migratory chops to go walk for your grass. I can tell you that right now. If you want to see migrators like grass seekers, take a look at wildebeest. Take a look at some of those African herds. They migrate like forever just to find a little bit of grass. They don't want to do that. They would rather just have it all right there, just chomp on it, right? But that's not the way it happens. So what do? We hang on to it, right? Save it for a rainy day. And that's exactly what you're doing with polysaccharides. What you're doing is you're doing energy storage. Why? Because carbohydrates are the body's primary energy source. I'm going to call it a preference because it is a preference. So what your body wants is it wants carbohydrates. That's what it wants. And remember, when we're talking about laying down our energy plan from the get-go, our big biological question of life, energy is hard to come by. So the last thing you do is squander it, right? So that's the last thing you do. Otherwise, you're going to be in serious deep trouble because you know the tough times are coming for you. It's not a matter of if, it's a matter of when. They're coming for you. So the question is, are you ready for it? Right? That's the reason why when you're at Thanksgiving, I love Thanksgiving because it's like just, I mean, done right, you shouldn't be able to breathe on Thanksgiving, right? I mean, you should just be laying there like, somebody just give me oxygen, right? I mean, that should be about it. But you might roll over just to watch the football game. Again, football's involved. Notice the theme here, right? Yeah, so the whole gluttony party football thing, they're just naturally made in heaven for each other. Right, so the idea is you want to save this for a rainy day, and that's basically what you're doing with these polysaccharides. So you build a couple of them. You have essentially two different types that are essentially for energy storage. So these are nutritional. These are nutrients. So you have plant starches that will essentially allow plants to store up energy. Now, plants don't have to worry about gluttony. They're not gorging at the trough of the NFL. which yesterday did seem like a trough in all the. Stop. I'll stop. So I can go into the Chiefs like all day long. Broncos, I don't mind. Chargers, I don't mind. There's just something about the Chiefs that just rubs me the wrong way. Always has. It's Schottenheimer. For you Chiefs fans, it's the Schottenheimer years. That's what did it for me. Turned me into an insane person. But anyway, for plants, you're basically storing up your glucose, right? And as a plant, you're basically storing this for a rainy day. That's exactly what you're trying to do. Only you're just making it right directly from the sun. So you're able to make your own food. Animals, not so much. Animals have a separate type of starch that they make for themselves. They don't really make it. They consume it, and then they kind of put it together in these little clumps called glycogen. Okay, and then they store that in their tissues. For instance, in us, we have glycogen, not plant starch, right? So even the plant starch you eat, like if you eat a potato, starchy type of a thing, you take the starch of the potato, you break it down into glucose, and you rebuild it into your own glycogen reserves, and you pack those glycogen reserves in your liver and your skeletal muscles, right? So it's kind of like a little bit of a lunch, right? So you pack a lunch for your liver and for your skeletal muscles. But it's clearly an energy strategy, right? You're saving it, you're using it for the purpose of energetics. Now, that's to be compared to more structural carbohydrates. So these guys are structural in nature. And there's a couple of major types. So for instance, for plants, they have cellulose, which is also made of glucose, but basically this is the fibrous portion of plants. And it's a component of the cell wall. Matter of fact, you see cellulose everywhere, every time you eat a plant. Anybody ever eat a plant before? Anybody salad lovers? I love salad. One of my favorites is just spinach. I just could eat spinach all day long. I love spinach, right? So when you're eating spinach or lettuce or whatever, any kind of a plant, you're basically crushing those plant cells. Remember looking at Eladia? Those like little rectangular cell walls? That's what you're eating. You're crushing those cell walls. There's cellulose in those cell walls. That's what creates that kind of rigid, kind of cubical look, right? That kind of rectangular look of the cell walls of the Eladia. And in a spinach plant, you're just basically tearing that apart. You're shredding those cells and you're liberating all the cell guts. Kind of sounds sick at that point, right? It's like gross. It's like your mouth is full of spinach guts. Yes, and delicious spinach, right? So, right, and then that's what you're eating. So you're eating part of that cellulose. How many celery lovers do I have? Personally, I love celery. How many of you guys really love like that little fibery part of the cellulose where you can like floss your teeth with it? Not so much, right? Actually, half the time you have to floss your teeth to get it out of there, right? It's like a little souvenir. Kind of suck on that little string all day long. If you don't have floss, of course, right? You guys are like, okay, dude, seriously, this is too much. But no, what is that little string? It's cellulose. So that fibrous portion, indigestible portion of the plant is cellulose, and we eat it all the time. So this is indigestible. Both of these guys are indigestible. What? Yes, matter of fact, the cellulose that's in plant matter is insoluble fiber. That's typically what you're looking at. And the reason why it's good is because the idea is if you have a little bit of that fiber in you, it has almost like a steel wool effect, a gentle steel wool effect as it goes through your system. It kind of like sort of scours. It doesn't really scour, just it kind of moves stuff through. So you pick up all those particulates and things like that. It gets balled up into that insoluble fiber, then wadded up in a nice little turd, and then out it comes.
Corn the same?
Yes, right? The husk of corn, right? So if you just swallow corn whole, like a corn kernel whole, like soft corn, not like hard corn, but soft corn, swallow it whole, it's you got to polish it up a little bit, but it's going to come right back out like cleaner than it went in, because your intestines will have cleaned it all up. But why? It's because the husk of the corn kernel is cellulose. It's only if you bite it and get that little squirt of corn in your mouth That's the starch. That's the digestible part of it. So in this case, the corn takes its little liquidy starch and puts it inside a little case of cellulose. That's the reason why you should always chew your corn, unless you like seeing all of your corn floating around in the toilet. And if you do, that's fine for you. I don't need to know anything about that. Just saying that's why that is, right? So it's not like your digestive system is on the fritz or anything like that. That's normal. You don't digest cellulose. It just passes right on through. Okay. Just kind of as a little bit of an outlier, another example of where you see cellulose, which is kind of like a bit of a range, is wood. Right? I mean, we all see wood all the time, right? We see trees, they're hard and woody. Well, that wood is actually cellulose. But typically when you're taking a look at a tree, it's cellulose, but it's a little bit different, right? Because if you ever take a look at a tree, you ever cut a tree, you know that in a tree you have the center portion, which is the heartwood, right? That's like the soft, wet stuff. And the reason is because in a tree, the vascular system of the tree, where the water's going through, is all in the center. As it grows outward, it adds new cells and it adds new layers to it. It pushes everything out, but those outer layers that are getting pushed out go through a period of death. So they don't all live. Those cells that are getting pushed out, they lose contact with their supply lines, which is all here in the center, and then they die as cells, but their cell walls are left behind. So they're like a little chamber. And then what the tree does is something amazing. This is the woodiness of a plant, is they fill those cellulose walls with a protein called lignin, which is like cellular cement. And it creates it's already a fairly structural cell wall and turns it into really, really hard, robust cell walls. So that gives you that hard woodiness of the actual wood itself. So really, when you're looking at wood itself, you're looking at a series of lignified cell walls that have since died because the outer rings have long since been dead. They've long since lost contact with their central supply lines, and they've been filled with this cement-like lignin, and so they're just all hard now. Okay. That's what causes plants to become woody. Okay. So that's another example of where cellulose. So you can see just in the cellulose spectrum, you can see there's lots of variation, especially in the plant world, of where you deploy cellulose, different ways you can deploy cellulose, and how you can create structure with cellulose, right? The other one and the last one is chitin. So this is kind of a structural carbohydrate, but this one contains nitrogen in it, so it's a little bit different. That's not common to have nitrogen in there, but it does. And typically where you see this is in the skeletons of insects, arthropods. So those little exoskeletons, those are chitin. That's a structural carbohydrate that their little exoskeletons are made out of. You also see this in fungi. So like the body of a mushroom, the firmness of a mushroom is chitin. So it's a carbohydrate, it's a structural carbohydrate. Okay. And so you can see how that carbohydrate gives you structure. It's not great, is it? I mean, we wouldn't build our skeleton system on a structural carbohydrate because it's too spongy, right? It doesn't have enough strength and power to it, like structural steel, right? We need something strong, like structural steel. This stuff is good if you got a little body, like a mushroom, for instance, and if you're not going to get very hot, so the gravity doesn't collapse you down under your own weight. So for you, having like a little carbohydrate skeleton is just okay. For an insect, typically fairly small, having that little bit of exoskeleton is fine. By the way, if you want to play exoskeleton games and you have the a bent toward the macabre, is feed a fly to a spider and then kind of let the spider have its day with it, let it a week or whatever. I mean, just let him do whatever he wants with it. And then afterwards, when he's done with it and he's clear that the spider's moved on to some other hunting grounds or whatever, is take a look at the fly that's left behind. We've all done this, haven't we? Have you ever cleaned out a windowsill and you kind of see this little fly in there and it looks like he's alive, but then you kind of go to crush him and it's just like powder? You know what happened there? Spider got him. Because all he is his exoskeleton. That's all it's left. Because all of his internal organs are inside and attached to the inside of his exoskeleton, like a shell. So what happens is a spider will suck his juice out, essentially, right? So essentially what a spider does is when they bite the fly, they don't bite the fly necessarily to just paralyze it or kill it. They actually are injecting hydrolytic enzymes in there. And of course, we heard that term before, haven't we? Hydrolytic water cutters. So what are those hydrolytic enzymes doing to the macromolecules? Yeah, they're tearing them apart, right? So they're turning this fly from DNA, protein, lipids, and carbohydrates into essentially a slurry of monomers. So then eventually what'll happen is you got yourself a little milkshake, a little fly smoothie. And that's what the spider drinks for its own molecules, right? This is also the reason why, have you ever noticed that when a spider kills or does the initial bite, you notice what it'll do, it'll kind of like, sometimes it'll wrap it up if it's a wrapper. Sometimes it may not. It'll just leave it there, but it'll just take off, right? It'll just like leave and it'll be like, wait, but don't you want to eat them? Right? Do you know why he leaves? Exactly. He lets time for the enzymes to break everything down so that when he comes back, there's not a bunch of chunks in there, right? It's just a nice, smooth. And then, of course, when he's done sucking it all out, what's left? The chitinous exoskeleton. That's it. So what you find in the windowsill is an empty shell of a fly. And so when you go to like pick it up, it just turns into dust. Why? Because that's the chitin that you just picked up. Think about that next time you see a husk of a fly. Or when you see a spider. What? The chitin is not. No. No, can't digest it. So let's then take a look at how these polysaccharides are constructed, shall we? We already know that they are a series of glucoses. There are a lot of glucoses in a line. And so what we want to do is we want to take a look, first of all, at the plant starches and the animal starches. So the digestible ones. These are the nutritional ones. Right, we're going to start off, first of all, by using from our palette of materials, right, our little list of building blocks to work with. We're going to pick out alpha glucose. And then what we're going to do is we're going to hook these alpha glucoses together in 1,4 linkages. That's these guys right here. So these are the alpha 1,4 linkages. And it's going to form end to end, right? So here's your number 1 carbon to your number 4, number 1 to number 4, and so forth. Number 1 to number 4, as far as you want to go. Now, when you're linking these guys end to end in these 1,4 linkages, what you start to create is this long chain. And so here you can see that when you're linking these alpha glucose together, when you kind of link them together, the way that they're sort of structured, this shape-wise, the way they kind of like orient themselves, is they kind of form this like little corkscrew shape. And this little corkscrew shape is kind of what we think of as plant starch. We call it amylose, right? Notice the OSE suffix, right? Everything that ends in OSE is a carbohydrate. So this is your plant starch. This is basically your regular plant starch, amylose. Now, in some cases, amylose will form a branch, a side branch to it, right? So that's where you basically do this 1,6 linkage. So here you can see, here's your number 6 carbon. And then you're going to be adding from the 1 carbon here to the number 6 carbon of the growing chain, right? So here's your chain here, and then you're going to link this to the 1 carbon to the 6 carbon. This is going to be your alpha 1,6 linkage. Notice you form the side chain, and the side chain can then be added to and form its own little side chain. Now, when you do that to amylose, it's referred to as amylopectin. Also a carbohydrate, one of the few that doesn't end in OSE. Okay, a fruit pectin oftentimes is a type of branched plant starch. Okay, so that's what you're talking about there. This is one of the reasons why, like, if you're in culinary practice, what do you use fruit pectin for? And usually, like in the dessert dishes or things like that, right? You usually will use it as a way to sort of thicken up something, right? It's a thickener. Well, guess what else is a thickener for you gravy makers? Cornstarch, right? You can thicken up a soup by adding what? cornstarch, flour is an alternative, right? So some of you might use, but you can also use cornstarch. So it's starch. They have something in common in the sense that you have this sort of starch, fruit pectin. So they're both thickening agents. So you can basically make a thicker sort of a consistency instead of just like a runny liquid. Okay. But that's what fruit pectin is. It's amylopectin. It's got a few branches, but not a lot, right? Most of it is like the long linear chain, but you have an occasional branch here or there. And so that's kind of helpful. But then what we want to do is we want to compare it to the animal version, right? Glycogen. Now, glycogen basically goes to town on branching. That's what animals do. So let's take a look at, here's our chain, right? And then what we're going to do is we're going to start adding a bunch of branches. And this is what animals do. So here's a side chain. I'm going to add here, add one here, add one there, add one there, add one there, add one there. And there's another one right on there on the tip. Maybe one right there. And then I'm going to start adding side chains to my side chains. And I'm going to start adding side chains to the side chains to the side chains to the side chains. Get the idea? All of a sudden, it's getting kind of hard to see where the original chain was. So if I didn't draw it in a slightly thicker line, you wouldn't even know that that was the original chain because you've got so many side chains here. Like if I were to write these a little more thicker, it wouldn't be so obvious, would it? So as a result, what you have is you basically have this dense cluster that we refer to as a glycogen granule. And when you take a look at, this is an electron micrograph, a transmission electron micrograph of a liver cell, but these little black grains right here, these are glycogen granules that you've stored in there. Now, why do animals do this and not plants? Well, there's one easy reason why. Animals, we don't have anywhere to put it. If we make a starch, we don't have anywhere to really put it. So what that means is we need to make sure that we have this starch packed into a really tight, dense capsule so we can pack this into an area and save space. Because here's what a plant does. A plant says, oh, okay, let's just go ahead and take a root. We have plenty of roots. We can spare one. And let's just start filling this root up with starch. And this basically just gets to swell up with starch. And then pretty soon we call that a potato, right? Or let's just take a modified stem, right? Or an offshoot of a stem, like a modified branch. And let's just start building this big club-like structure of starch on there. And then that would be like a modified leaf, right? So it just becomes, so they have structures that they can create and they can just modify it. They can just be like, hey, I'll just fill this up with starch. I've got extra roots. I don't need this one. We don't have that, do we? I mean, what are we gonna do? Oh, you know, I got two pinkies. I'm gonna make this one my little starch reservoir. So I'm gonna have this big old club of starch on the end of my hand. Imagine trying to play the piano with that. Not so easy, right? So we don't have a lot of gratuitous structure that we can just say, oh, well, let's just dump all of our starch there. That's gonna be our starch organ. We don't have that, right? So what we have to do is we have to pack all of our starch into a very tight package so that it can exist, for the most part, free of trouble in already pre-existing structures. The best place for that, liver, right? And then alternatively, the skeletal muscle. So these are just like small little reservoirs. We're not talking about a massive amount, Okay. Oh, but wait, the plants have a long-term storage strategy, don't they? How many of you have ever grown potatoes? So if you forget one in the ground, what happens next season? Yeah, you get a potato plant back, right? You're like, okay, I think I got all the potatoes. But potatoes are fun because it's like, you know, you missed something, even just a little itty bitty guy, right? That's enough to do what? To sprout the next generation, right? And then pretty soon you have all these potato plants sprouting up all over the place. And it's like, okay, I guess I missed a few, right? And then of course they do what? They do the same thing. They grow up and they become plants. They make all their carbohydrates. They store it in their potatoes, and then you do the same thing. This is what tuber types of plants do. That's one of their strategies for survival. Is the plant itself is busy making these starchy structures underneath the ground, and that becomes the food source and the energy source for the next generation to sprout from and to create more. And that's how you spread around. Okay. And if you've ever lost control of potatoes, you know that they start to like spread everywhere. And it's like pretty soon you've like got this whole potato patch. You're like, okay, I guess I'm losing this battle here. So you backhoe out there and you just had to dig them all up, right? And you find out that the culprit wasn't some big old monster potato. It was like some little itty bitty guy that's like almost impossible to find in a garden of size. So you're screwed, right? This is the reason why a lot of people do basket gardening with potatoes, because all you do is just dump it all out on the ground and you got everything there. So you're good. But that's their long term, right? That's there for the next season. Do we have a long term? Not in the carbohydrate world, right? I mean, the liver is about as long as it gets. But guess what? The liver's got to do other things too, right? So it can't just have a bunch of starches all hanging around. It's like, guys, listen, do something or get out of my way, because I've got an entire body's worth of metabolism to run here. So if you're not going to do something productive, then you need to get out, right? So what's our long-term storage? This is just to complete the energy thing. Oh, it's very simple. You Thanksgiving glutton, you. Where does that extra glucose go first? Into starches, right? Oh, but how soon is it going to be before you fill up your liver? Right, your liver is not an infinite source. It certainly doesn't have the capacity to fill itself up with an entire Thanksgiving dinner where you nailed down 3 different species in one sitting and wiped out probably the better part of Village Inn's pie inventory. And that was before the Thanksgiving meal. And you guys are like, is this like self-confession day for you? It's like, it's not actually. I used to do that when I was a teenager, when I was a ravenous beast, but not anymore. Why? Because I'm spending the rest of my life trying to work it off, right? The saddlebags they merge together into a tire, and then I go 4-wheel drive with it, right? So, and put the spare in the back, right? So it gets worse, right? So at that point, yeah, so I try to behave myself. So it's planned gluttony, right? So I'll gluttonize myself between 3 and 6, and then I'm out, right? So I got to step back. But anyway, that's that. So what's ours? Well, I mentioned it, didn't I? Where does it go after you fill your liver up? Oh, yes. It goes to our insulation, right? So it goes to the saddlebags, right? It goes to the tire. It goes to the spare. I mean, and it fills up, right? So that's where it goes. So what happens there then? Is that your energy supply there? Sure it is, right? Lipids, mostly hydrocarbon, actually. So we already know there's lots of energy in there. But is your body going to let you have that? If you start running on the treadmill on January 1st because you realize what you did to yourself from about Thanksgiving on, which we oftentimes do. That's a fairly American pattern, right? One extreme neutralized by another extreme, which is then recorrected by the other extreme, right? Because Mardi Gras is right around the corner. So it's like we go gluttony, guilt, gluttony, guilt, right? When Passover, Easter happens, right? That's when the Lent thing sort of, that's what Mardi Gras is about anyway. I'm not Catholic, but that much I do know, right? Because Ash Wednesday is right after Mardi Gras, right? So you're supposed to give everything up. That's your guilt phase. And then what happens? Summer hits and we're back to gluttony again, right? So we kind of just gluttony, guilt, gluttony, guilt, gluttony, guilt. So this is a one pendulum swing to the other. That's the way we do this. But what's happening to your body? Your body's not letting it go, is it? You got to do a little bit more than run on the treadmill a couple of minutes a day for a month before you finally quit during Mardi Gras. This is your energy supply, right? This is basically what your body needs to survive. And it knows that. So this is your long-term storage. Think about it this way. Think about glucose as your energy. Pure glucose, the monomer, is by far your body's preferred fuel source. If you feed your body disaccharide or monosaccharide, preferably, that is all it will burn. So if you're eating a Snickers bar while running on the treadmill, you might as well sit on the couch because you're doing nothing. Because your body is only going to be burning that Snickers bar. It's not until it exhausts all of the free carbohydrate that it then will grudgingly move into short-term supply and be like, okay, I'm out of free glucose. Now what? Well, I'm glad you asked because we've got a pantry full of glycogen. So let's start getting it out there and keep those engines burning, right? But guess what? You don't have a deep reservoir of this, do you? This burns out pretty quickly too. And then what? Only then will the body then grudgingly go after fat. Because this is your long term. Matter of fact, in some cases, it'll actually rather go after your protein than fat. And that's not a good thing, right? If you've ever worked out and you have the smell of ammonia in your nose, that's deamination of your proteins. That's your body metabolizing proteins. That's not a good metabolic pathway to be using. So if that's where you are physically, like when you're working out, you need to start changing some of your workout and change a little bit because you want to make that's not good. You don't want to chew up your proteins. Okay, you want to chew your fat up, not your proteins. So basically, I like to think of it in terms of economics. This is a really great way actually to think of energy, right? Think of the free glucose as cash in your pocket, right? If you need to eat right now, what are you likely going to reach for first? Cash in your pocket, right? It's absolutely liquid. You've got it. You're ready to roll. Slap that baby down. You got yourself some food, right? But what if you don't have any cash in your pocket? Can you still buy food? Sure you can, right? It's called a bank because chances are you have a bank account, which is short-term storage, secure, a little less accessible, but still you can get to it, can't you? Some of you guys have a debit card. That's just like cash. Some of you guys need to make a run on the ATM, right? So that is more secure, less accessible, but still you have access to it. However, the long-term storage, so if you drain your bank accounts, then what are you after? Your investments, right? So if you've got mutual funds, 401ks, IRAs, things that you're not supposed to touch until you're 59 and a half, which for some of you guys is going to be forever, right? Because you're like barely 5 and a half. Yeah, right. A house, right? We're like, listen, we don't have a choice. We got to sell the house because, I mean, it's better to sell the house than to go into foreclosure because you're going to be kicked out of the house one way or the other. So you might as well do it and get some money back, hopefully. Right. So these are things where, what do they say? Can you get into your 401k? Sure, you can, right? But there's some heavy penalties associated with that one. So if you're getting your 401k, the idea is, listen, you are in some deep, deep kimchi here. I mean, you're in serious trouble if you're having to tap into these long-term financial reserves because they're not designed for you to have right now. These are your storage for long-term. When the famine hits, when the rainy day hits, when you no longer have a steady income because you're retired, that's what these accounts are for. This is the reason why you don't want to touch it and why it's hard to get a hold of it. It's designed to be that way. This is your long-term storage, right? Your saddlebags and your spare tire. And that's the reason why it's so hard to get rid of, is because it's like designed that way. It's your 401k. Don't touch it. You can if you're in serious trouble, but you're going to pay a price for it, right? Because the idea is to try not to touch it at all.
What effects do you have in your fast metabolism?
That in a lot of ways is hardwired. There's a couple of things. Your metabolism will have different rates at different points in life. As you're growing, your metabolism is raging. I mean, it's about as hot as it's going to get. So your engine is motoring along about the highest the speed it's going to get. So that's the reason why, as a teenager especially, you pretty much eat everything that is, slower than you. I mean, it's like if you can catch it, you're going to eat it, right? I mean, and there's like a bottomless pit of hunger as a teenager. I mean, teenagers generally can eat until they are in a coma, and then they'll wake up and continue eating, right? And so, I mean, that's just part of it, and that's your metabolism is like really, really high. And notice when a teenager does that, a lot of times because they're growing so fast, their metabolism is so high because they're supplying a lot of energy for their growth spurts that they're having. Is their metabolism is really high. I mean, it's motoring at a high speed. This is the reason why a lot of times teenagers don't gain weight. They eat tons and they don't gain anything, and that persists. I mean, your metabolism slows down, but you're able to eat and not gain weight for the most part, relatively speaking, right? Through your 20s. It's around your 30s and 40s that all of a sudden your metabolism is like, okay, we're slowing it down. We're downshifting, right? And then all of a sudden you have that, breathless Thanksgiving glutton fest, and you realize that it doesn't go away. It like, you're still looking at Thanksgiving in the mirror, like on New Year's Day. Right. And then you realize, oh, I guess my metabolism is slowing down. So I guess I probably better kind of tone down. So there are natural speed rates of metabolism that change during life. Now, one person's relative rate versus another is hardwired in their genetics. So there's a very strong genetic component to how one person's metabolism is wired versus another. Which is one of the reasons why when you take a look at like struggles with obesity and things like that, especially with the shifts in metabolism, right? I mean, there's like people who are still like in their 50s, they can pretty much eat whatever they want. They don't really gain a ton of weight. And there's other people who eat the same thing and they're just like, right? And some of that is just hardwired differences in the way their metabolic rates are wired. Some people are they have a higher motor. Their basal rates is just wired higher than others. And there's a lot of genetics that goes into that. So that is true. But that's metabolism, especially basal rates, metabolism is tricky because it fluctuates so much and there's so much variation. But yeah, that's always something to keep in mind, right? So like if you're working out or something like that, or you've got a physical trainer or a nutritionist and and you're like in your 50s maybe, right? And they're like in their 20s. And it's like, you know what, why don't you actually age good 30 years and then you tell me how much everything you just said makes any sense? Because I can guarantee you half of what you just said is out the window. Because until you've been slammed against the old age wall and pretty much worked over by it, then you don't really know what you're talking about. You can talk to other 20-year-olds, that's fine. But you can't really say much to somebody who's in a totally metabolic reality difference than you, because you don't know. So just remember that. Okay, those are the nutritionals. Yes, let's take a look at the non-nutritionals. Now we're going to do something different. These are the structurals. Remember, these are the indigestible ones. This is this is not the chitin. This is like the cellulose fiber one. In this case, we're going to do something subtly different, very subtly different. In this case, we're going to choose, instead of alpha, we're going to do beta glucose. And we're going to do the same thing, by the way. We're going to do, they're still the same, 1 to 4, 1 to 4, 1 to 4. Same glycosidic linkages that we had before. The only difference is they're beta now instead of alpha. So what does that do for you? First of all, what that does for you is when you have a series of beta, because of the orientation of the OH group above versus below, what's going to happen in this particular case is when they come together in this sort of end-to-end fashion, they don't form that little corkscrew. They form straight lines. And that's helpful. Why? Because what'll happen is you can actually pack these individual straight lines of cellulose and you can pack them together and you can create a nice rope-like fiber by packing these guys together. And that's essentially what you're looking at here. This is a cellulose fiber that you see in a plant cell wall. And that's actually a scanning electron micrograph of the cellulose fiber. So you can see it looks like a little rope. It looks kind of like a little rawhide rope, right? Which is actually a pretty strong, sturdy rope. But here's the thing though, remember we said that you can't digest the structural cellulose. You can't digest this. So the question is why? And the answer is very simple. We simply don't have the enzymes. So let's take a look at the enzyme that we do have. We do have the enzyme to digest regular starch and glycogen. So let's take a look at what that enzyme looks like. So the enzyme that will go after starch will have in it three-dimensional pockets called active sites, which are designed to three-dimensionally fit the molecule that it works on, in this case, starch. And so you'll see in these active sites, you'll see like a little three-dimensional pocket that fits one monomer, so that's good. And then it'll see this downward angle of the alpha glucose, and so it'll have a little pocket for that. Then I'll have another little pocket for the other glucose. You'll see the downward angle, so I have a little pocket for that, and another little glucose, and a downward angle, and then so forth and so on. And so notice how everything fits. It kind of fits in there perfectly, just like a right hand and a right-handed glove. Now, the problem is this is the only kind of enzyme you have. You don't have an enzyme to fit for a beta linkage. So let's use this enzyme then and see how it fares against cellulose. So here's the same enzyme. In this case, I'm going to have a pocket that's going to fit my glucose. So far, so good. And I'm going to have a little down pocket that's going to fit my downward angle. So far, so good. A little pocket for my glucose. So far, so good. And then I'm going to have a downward pocket for my downward angle, but my angle is going the opposite direction. So I've got a mismatch here. And the same thing is true. So this one will fit, the next one will not. So you notice this right here is enough to throw the enzyme out of whack. Just like a glove, right? If I were to put the right-handed glove on the left hand, would it sort of fit? The fingers would kind of fit, right? It'd be a little weird. I mean, the pinky would be in the index hole. These guys would be a little bit different. This one would be a little tight, but I can kind of fit it in there a little bit. It kind of fit the fingers, but the thumb would have nowhere to go, right? So that's enough, even though that's it, right? I'd be like this. That's enough to say, no, this is that. This is no, this is it. This is not it, right? That's enough here. Just having that mismatch in that pocket is enough to say, listen, we can't do anything with this, which is the reason why you can't digest cellulose and why it passes on through.
Where is that mismatch? It's like.
It's, well, in an enzyme, they have three-dimensional pockets in the protein itself, and they're designed to fit the substrate. So this guy right here doesn't have a fit because his bond angle is going the opposite direction. It's supposed to fit in that little nook. So, and since it doesn't, then that's a mismatch, and that protein can't do anything with that. So that's enough to basically, no, we're off the table now. All right. And as a result, then you don't have the ability to digest cellulose, which is the reason why you can't eat wood and things like that. Oh, but wait a minute. Aren't there organisms out there to eat wood? Who are they? Termites in particular, right? Because they're the hardcore. Cows, they don't really eat wood, they eat stuff. But termites in particular, right? So the question is though, aren't termites eating wood? Can't they do this? And the answer is no. The only reason why they can digest wood is not because they have enzymes for the cellulose in the wood, but because they have bacteria in their gut that do. So the bacteria will attack the wood, break down the wood, and once you liberate the cellulose, the beta and the alpha separately, like by itself, you're good. So if you drink, if I gave you a glass of just like pure beta glucose, not linked together at all, you drink, your body would look at it just like alpha glucose. It'd be like, thanks for the sugar shot, right? And you'd be like, right, like that. And so that's fine. But the second I put it together is when you can't get to it, because that's like a terminal linkage. You've created a polymer. Now you can no longer, you can't break it apart because there's no fit. That enzyme doesn't work with that one. But the bacteria in the termite gut do have that enzyme. They break it apart, and then the termites are able to use the free glucose. Okay. That's how they get to the wood. Okay, so that's the end of carbohydrates. Now, what about the best one of all? Well, it's actually not the best. It is pretty good. I have to admit, the proteins are pretty good. Nucleic acids, I'd have to say, are the best. But man, the proteins are hard not to love. Why? Because proteins basically do everything. Think about one function in your body. Name one. Proteins, right? In order to digest food, you need hydrolytic enzymes to digest it and to break it all apart into your monomers so you can absorb it. And you have proteins. Those are proteins. Those enzymes are proteins that do that, right? Proteins. Actually, most of your muscle is protein. So myosin is protein, actin is protein. The structure of your muscle is actually made out of. That's all protein. Right? So pretty much anything your cell does, anything your body does, the proteins are the ones that are doing all the heavy lifting. So these guys are the workers, which is one of the reasons why if you took a biochemistry class, like typically a biochemistry class would be like studying on a much more quantitative level, all four of these major groups all semester long. But the lion's share of biochemistry studies and research is all on proteins. Proteins are mostly, and DNA. Those are the two that consume most of our attention in biochemistry because everything is done by proteins. They are the worker bees of everything. And then DNA and RNA like the queens. They just basically, they're the ideas people, right? So I'll come up with the idea, but you guys do all the work, right? That's kind of what DNA and RNA is like. And then proteins do all the work. They can be. They can also be super simple. So they can have quite a bit of range in terms of size and structure. But they're probably not as complicated as you think, at least initially. It depends on the protein, of course, you're looking at. Okay, so what do? Well, they do this, right? They do enzyme stuff, right? So they run chemical reactions. They can do defense, right? I mean, antibodies, for instance, those are proteins. Transport, they can move things in and out of the cell. Metabolites and things like that, right? Things that your cell needs or needs to get rid of. It can also do support. So it can actually be a structural support system for the cell itself. And we'll talk about each of these and we'll see examples of these as we kind of move through especially the next chapter. Motion, right? Any cell that needs to move around, proteins are behind it. This is how you move. How about regulation? You have an entire system based on this one, right? Your entire endocrine system, which is your system of hormones that organizes and regulates all of these chemical reactions, typically that are driven by enzymes. A lot of those hormones, not all of them, but a lot of them are peptide hormones, that is protein in nature. Okay. So, and of course, storage. So proteins can actually be a storage solution for something like lipids, for instance, right? How many of you guys have ever heard of a type of protein called a lipoprotein? Let me ask this question. How many of you guys have ever had a lipid panel done? Like you've gone to the doctor and you've had your cholesterol checked. Okay, then you know what a lipoprotein is. Because actually what we check when we do cholesterol is we don't actually check cholesterol. Cholesterol is a steroid. It's a type of lipid. We'll talk about that. But steroid that's not something we can actually check specifically. What we check are the proteins that carry the cholesterol. It's like a carriage case. And those types of proteins are called lipoproteins. Lipo, fats, lipids, proteins. These are proteins whose job it is to carry lipids around. Why? By the way, in your blood plasma, you have lots of these types of proteins. They're called shuttle proteins. They oftentimes will carry lots of different types of lipid molecules around. Why? Why not just let your lipids float around in your blood on their own? What? Well, they're going somewhere. They technically could get to somewhere, but what would it look like? What would your blood look like if you just let lipids float around and they're free without help? Yes, right. It would cause blockage. It's oily. It's thick, right? So it would look like water and vinegar. I mean, water and oil, right? Remember the whole hydrophilic, hydrophobic thing? What's your blood mostly made of? Yeah. And how do you think a lipid is going to fare in blood? Is it going to fare very well? No. So you need lipids though, don't you? So you have to have a strategy to get them to where they need to go. Who does that for you? The lipoproteins. These storage proteins that basically grab onto them and store them. So if they kind of sequester them inside of themselves, they themselves are friendly to water. So they can be dissolved in water and be happy in water, but they kind of have all the lipids that are kind of all clustered underneath them, like a mother hen with the chicks under her wing, and kind of have them all clustered in there. And so the idea is the more of these lipoprotein molecules you have, the more cholesterol molecules you have, because the idea is the more cholesterol you consume, the more your liver makes these lipoproteins in order to handle that cholesterol load. So it's a one-to-one relationship. The more you're eating dietarily, the more these lipoproteins you're going to have, which is the reason why we don't check cholesterol. We check these lipoprotein levels because it's a one-to-one relationship. So this is basically what they do. And there's obviously other things as well that you can kind of toss in there as well. But they do a lot of work. They do pretty much all the work. So now let's take a look at the structure of the amino acids and what they're composed of. So first of all a protein is polymerically is essentially one long branch of its monomers, which are amino acids. Where we already talked a little bit about amino acids, where we talked about the functional groups. So we talked about those. And so we have a couple of different areas associated with the amino acid, where we talked a little bit about having the amino group on one side. That's this guy right here. And then on the other side, we have the carboxylic acid group. So that's that COOH group, right? That's what creates the amino acid component. And then we have a central carbon, which is in the middle, sandwiched in between the amino group. So that's this guy right there. And then to that central carbon, we have two different things attached. We have our hydrogen. That's this guy right here. And then, of course, we have our R group, which has 20 different possibilities. All amino acids look the same, with the exception of that R group, right? And there's 20 different possibilities there. So when you take a look at amino acid itself, since they all basically look the same, yes. Yep. So since we take a look at amino acid, they all have the same basic common system, right? The amino, central carbon, acid, amino, central carbon, acid. The only thing that differs between all of them is the nature of this R group, this side chain. So the question is, what are those side chains? And how do they dictate the personality or the chemical temperament of the protein itself? And that's basically what we get to, right? So these R groups are what defines one amino acid from the other. So there's a couple of major functional categories that we can put amino acids into. The first group is the non-polar group. So leucine is just an example of one, right? So this is basically a group where the R chain, the R group is a non-polar type of a side chain, right? Now, what do we expect to see if it's non-polar? Lots of carbon-hydrogen bonds, right? And that's exactly what you see. The other one is polar uncharged. 3 is the example here. If you're polar, what are you likely going to see? Either charged, well, this is uncharged, right? So you're likely going to see the electronegative atoms, aren't you? So you're going to see a combination of oxygens, which is electronegative, or nitrogens, which is also electronegative. This would create your polarity of your side chain. Then we have the charge, right? This is where we're going to either have positive or negative charge. And basically, this is acidic or basic. And it's kind of pH or its acidity characteristics. And then we have a special one, aromatic. So these basically are characterized by a benzene ring or some sort of a ring structure, right? So the aromatic, by the way, is, remember when I said that benzene ring, remember we saw that on the functional groups list? That benzene ring has its own functional group in organic chemistry that you study. They call that special group the aromatic group, not because it smells good, but because that's just the word that they use to sort of characterize benzene itself. So that's kind of its own thing. So we're talking about aromatic as it referring to benzene. So it's got this sort of ring-like structure to it. And then of course you have some outliers with some unique structures, right? Proline, which is kind of a ring-like structure, but it's not really aromatic in nature. And you have cysteine. Remember cysteine? Cysteine is that one that has a sulfhydryl group on it, the one that's able to create those covalent cross links between two pieces of the protein backbone. So these are the different types of amino acids that we kind of categorize, and this is what they look like.
It's gonna be posted before Wednesday.
Yes, I'll probably post this. It depends on when it processes. No. The cutoff is before
Oh, yeah.
this starts, but I will try to post it like early on because some of the stuff will kind of help tie some of that other stuff together. So in case some of the early parts of this is helpful, so I'll try to get it posted. It depends on how quickly Zoom processes it, honestly, by the time you guys are done. So this is them. Wow. Okay, first of all, keep breathing. Right. Just inhale, exhale, right? So no, the answer to your question that you want to ask, but you're afraid to ask is no. I'm not going to have you memorize all of these. In biochem, yes. General chem, no. The only reason this is here is just to kind of show you visually how these different guys sort of slot together in their families of characteristics. And there's a reason for this, by the way, because the way a protein folds is dependent on the personalities that you put in place. And those personalities are given to you by the R chains, right, by these R groups. So let's take a look at this. So first of all, we're going to have the aromatics versus the non-aromatics. So notice going across here, you have basically side chains that all have this kind of ring-like structure with these alternating bonds. So notice you have the big benzene ring here, right? So that 6-membered ring with alternating double bonds. Same thing here. It's got a little home plate attached to it, but still basically the same thing. Same thing here. This one's a little weirder, but you can see you have alternating double bonds. So that's kind of get tossed in there. So these are the aromatics. These are the non-aromatics. So notice no ring structures in these ones. And these guys are the ones that kind of are a little on the special side. These are the outliers. So here you can see proline kind of has this little home plate, but it's all single bonds. So that's not very aromatic, right? Aromatic is you have to have double bonds in there in order to be aromatic, like benzene. So this one's a little bit different. The methionine, notice it has this sulfur group in there, but it's kind of like sandwiched by these two carbons, right? So it's a little bit different. It's not a sulfhydryl group. It's actually a different organic functional group that you get in organic chemistry, but we don't really work with it a whole lot here. But here's cysteine with your sulfhydryl group, right? So these guys are like unique. They're sort of set apart, and they oftentimes have special chemistry to them, right? If you want to think about, if you're a baseball fan, you can think of these guys as sort of like back in the old days when you used to have like very situational bullpen pitchers, you know, who would basically be specialists for like one particular hitter, right? Or one particular, like a lefty or something like that. And you'd stick them in for like one batter. And their job was to get that one guy out. That was it. Because that was the one guy they owned. But they didn't go further than that, right? You stuck them in for that job. They got that guy out, and then you pulled them out and you replaced them with somebody else. So they're very unique, right? They have a very specific function that's different than all the rest of the pitchers. And that's kind of what these guys are like. So when you put these guys in there, you got a very specific, unique function that you're trying to go for, like trying to create a disulfide bridge, for instance, with this guy. This guy here is the initiator amino acid. The very first amino acid of every single protein starts with this guy right here, methionine. And we'll talk more about that in the last chapter. We talk about the start codons and the process of making proteins. The other thing that we want to take a look at is their polarity. So going down, you can see the green is going to be these nonpolar. So that is, say, carbon hydrogen rich. The blue are going to be the polar uncharged. And then, of course, these guys are the charged, also part of that hydrophilic family, right? Because they're charged in nature. But take a look at these non-aromatic nonpolars. Notice they don't have a ring, so they're not aromatic like this guy here, but they're mostly carbon hydrogen bonds. All these R groups are all carbon hydrogen bonds of one stripe or another. That's what makes them nonpolar. The aromatics, on the other hand, are also mostly carbon-hydrogen bonds, but they just have that ring in there, right? That's what kind of sets them apart from these guys here, but they're still non-polar. If you take a look at the polar ones, notice what their R groups have in common is either or both an oxygen or a nitrogen, right? So for instance, here you can see an oxygen, that's going to make it polar. You can see this is an oxygen here, it's going to make it polar. This is an oxygen and a nitrogen, it's going to make it polar. This is an oxygen and nitrogen, which is going to make this one polar. And the tyrosine, you can see you drop this hydroxyl group on there, so that gives an oxygen that makes this one polar, right? Because now all of this electron density is going to be pulling toward that oxygen, making it a polar situation. So you can see they're not charged, but they have polarity to them, at least in the terms of the R group itself. And then in the charged ones, you can see the same basic idea, right? In this case, you have oxygen and nitrogen. Only in this case, what's going to happen is your oxygen species is going to be carrying a negative charge on there. Why? Because it got rid of a hydrogen, so that's why it's an acid, right? So it's kind of giving an acid off. So it's kind of gotten basically gotten rid of a hydrogen, so there's going to be negative charge. Nitrogens tend to be positively charged over here. So here's another negative charge in the oxygen, it's positive charge over here. You can see a little positive charge right there on the nitrogen. So this is the reason why the histidine basically goes along with these charged polar members, right? So now what does this mean? Remember, whenever you're setting this up, what you're creating are families of personality where each of these guys have similarities to each other, right? So for instance, these non-polars will have much more similarity to each other than with the polars. Now this is important because when you go to assign seats, when you go to pick which amino acid you want to put into place when you're making a protein, if you pick one polar and you put a non-polar next to it, you're going to be creating a lot of tension there. Why? Because we already know how much the hydrophobics hate to be around the hydrophilics. So the way you select these personalities and you put them in three-dimensional space together, that hatred, that hydrophilic, hydrophobic hatred is going to have a lot to do with how this protein folds. So this protein then is going to start folding up in such a way that the hydrophobics will run toward each other and away from the hydrophilics. And the hydrophilics will run toward each other and away from the hydrophobics. And the charge will basically run away from the hydrophobics. So you can imagine that if all these guys are linked together and they're like they're handcuffed together, you can imagine what kind of tension this is creating. They can't just run. But what they do is they contort like a bad game of Twister, or a good game, depends on how you look at it. Right? They do whatever they can to get away from these other folks that they can't stand. And that creates three-dimensional structure in the actual protein itself. If you're wondering, lab 3, the one we never got to, that's basically an illustrative model of that whole process itself. Which one?
On the very first one,
Alanine?
yes.
Well, see, they're all the backbone is always negatively charged, and the nitrogen, the amino side is always positively charged. Because they're so this is where this is the acidic part of it, so it can give up its acid, adopting a negative charge. Nitrogen being a base can actually adopt, so it can actually convert to an NH3 because it's got room for 3 bonding spots. But that would create a positive there. So there's a lot of characteristics in the backbone itself between this. This one here, though, is different because that is the R chain, the R group that's negative. So it's acidic, just like all the rest of them, right? So it's got the acidic side, just like all the rest of them. The backbone's the same for all these guys, and a positive, more basic amino side of things, right? But the difference is it's got this extra acidic side chain, which is the reason why it's acidic, or it's in that charge zone. Okay. Okay. So there's one thing I want to do. I want to kind of finish up the slide, and then I'm going to basically kind of go back to the slide to actually take a look at the 4 levels of structure, right? So when we're basically pulling together this amino acid, this is our dehydration synthesis, right? So we got to, let's see it. So we have our amino acids. These are our monomers. And we know how many of these amino acids we have, all 20 of them. And so what's going to happen is from your amino group, right? So in water, basically, this is going to liberate a hydrogen ion, which is the reason why it's an acidic, why it's an amino acid. But this is going to pick one up because nitrogen tends to want to accumulate one, whereas the carboxylic acid wants to release one. That's true of all acids and bases, right? And so when it does this, two of these hydrogens off of the amino group is going to combine with this oxygen on the adjacent carboxylic acid. And those two are going to be the components of water. So your enzyme is going to cut right there, the acid carbon of one, and it's going to cut right here and right here, where you have essentially the nitrogen of the amino side of the other. It doesn't have what it needs, right, at this particular point. So these two will go as water, and the carbon and the nitrogen will bind together to form the peptide bond. So this is the peptide bond. So the name of the bond that holds together carbohydrates is glycosidic. The name of the bond that holds together amino acids is the peptide bond, which is where we get that term pep from, right? So peptide, peptidase, things like that, things with pep on the front of it. That's basically associated with peptide bond. It's a protein thing. Okay. So what? For carbohydrates, glycosidic. Right. So what that brings us to then is the 4 levels of structure. And before we start the 4 levels of structure, what I want to do is I want to start with this one. And here's what I want to do. I want to build a tetrapeptide. And I want to start with that. Maybe a pentapeptide. I'll just start building it and I'll stop whenever I feel like we're good enough. Okay. But what I want to do is I want to build that first and then use that as our reference source to go through the 4 levels of folding. Okay. But that is a fairly strong topical shift. And that's a good place to start next time. Not on Wednesday, of course, because we have an exam, but next Monday.